So you might wonder, what can we do further with functions? It turns out that functions can be multiplied, they can be divided, you can add functions, you can subtract functions, and you can also apply functions one over top of the other. It's called the composition of a function. So this is lesson 5 in functions and relations, and we're actually going to the second page. The notation is kind of interesting. You'll note that we've been having some issues with brackets. So this is a double bracketed situation. And where you have to start is you have to start on the inside of those brackets. So you go on the inside, first you go f at x, figure out what that is, and then you're going to deal with g. So it's read as the function g is a function of f of x. I like the notation that's a little less bracket dependent, and that shows an open circle. G at f evaluated at x. This is especially interesting for calculus students, so we want to make sure that this makes sense to you. So the idea of a composite function is that there are two recipes that need to get applied. So we're going to go to class example 1 right here, and we're looking at h at x. And what I want to understand, or what I want you to understand, is how can I create that function h at x with two different recipes. So the two different recipes would be to say that one function, the f at x function, we like those letters, the f at x function is x squared. And then the next subsequent function, g at x, would be to take whatever the result was from the first function and subtract 2. So that's how it looks like. That's what it looks like in words and discussion. So f at x is x squared. So we take the function x and square it, and then we subtract 2. So the functions end up looking like what we discussed. The f at x takes x and square it. The g at x has to take the x squared and subtract 2, so that the g at x is subtract 2 from x. I want g at x to take the previous statement and subtract 2 from it. So writing the g with an x statement, the language changes a little bit. Let's take a look at this one. I want to try to express the function x plus 4 cubed as a composite of two functions. Probably easier to start in the middle. So my first function would be the idea of taking x and adding 4 to it. And then the next function would say, hey, let's take that and cube it. So first I'm going to take x and I'm going to add 4, so that I get x plus 4. And then what I want to have happen is I want to have the x plus 4 get cubed. So this needs to get cubed so that I get x plus 4 cubed at the end. So what are my functions? My functions need to be written in terms of x. So the first thing I wanted to do to x is add 4. And the g at x is going to take that x plus 4 and cube it. That's what I want to have happen. What does that look like in terms of a g at x statement? The g at x statement actually has to specifically tell me, take x and cube it. So I've flipped all the way to the bottom of page 35, and we're going to explore the notation that is the composite function. So the composite function, we're going to take a look at example number 4 down here at the bottom. What does this mean? This means I have to take g at f at x. And I'm going to work from the inside out. So I'm going to first replace that inside. The inside becomes what f at x was, 2x squared minus 1. And now I have to follow the instruction for what g says to do. And g says what you have to do is you have to take your function or your substitution and go 3 times that. I'm just going to move down here. 3 times 2x squared minus 1, and then subtract 4 off of that. And I can simplify that. I'm going to just buy myself a little bit more room. That's 6x squared minus 3 minus 4, which is 6x squared minus 7. Following similar logic, I'm going to translate the g at g and write it g at x. Follow those brackets. Go to the deep inside bracket and tell me what it is. G at 3x minus 4. So I replace the function with its actual expression, 3x minus 4. And now my instruction says, hey, go back and do that again. Go back to the instruction and go 3 times your x value, which this time is 3x minus 4, and then subtract 4 from that. Now this simplifies into something different. 9x minus 12 minus 4, which is 9x minus 16. So I'm going to leave that as our recording of composite functions. There is some work with domain and range that will come in our work. But if you take a look at your pink sheet, the assignment for lesson 5 is the following. 3AC, 4B, 7 through 9. Just do the B's on those. And then 10, 11, 13 to 18. So hopefully we'll see you all tomorrow. I know a few of you are gone, but you can access this. Remember, we've got a little bit of catching up to do, and I hope this allows us to feel prepared for functions.